Hi, I'm Satoru from AIST Japan. This work, Contour Preserving Melody Conversion, is joint work with Masataka Goto. Contour Preserving Melody Conversion achieves an intuitive melody composition. Say there is a melody and an accompaniment, and we extract the melodic contour from the melody. Let's have another pair of melody and accompaniment, and this time we reuse the accompaniment part. Contour preserving melody conversion can add up these two and generates a new melody with the given accompaniment. This conversion has two main features. First, the conversion preserves the melodic contour. We follow the definition of melodic contour by Walter J. Dowling that melodic contour is a sequence of single pitches that resembles the original intervallic patterns of a melody. He also points out that it can appear with changes in intervallic detail. Now I would like to play the results by our method. This is the original melody. And combining with a different accompaniment, we obtain this. As you can see, the melodic contour remains the same, except for a slight change in the second measure. Second, the conversion adjusts pitches to fit the accompaniment. It maintains consistency between melody and chorus. The available pitches in the melody are governed by the key, modes, and chords. Therefore, when generating a new melody, the pitches should be adjusted accordingly. Here are the examples of the conversion results. Let's say we would like to convert this G minor melody when its melodic contour is attached to a C major accompaniment. We obtain this. When the accompaniment is D minor, we can generate this. We can see the pitches are not only transposed, but also adjusted to fit the accompaniment. As for technical issues, we need to solve three issues. The first issue is how to reflect a melodic contour to a melody. The second issue is regarding how to maintain consistency between melody and an accompaniment. And finally, the third issue is how to achieve both of them. We will discuss these issues one by one. To reflect a melodic contour to a melody, we have designed a probabilistic contour model. Reflecting a melodic contour can be regarded as imposing a constraint on upward or downward pitch motions. As a melodic contour allows slight differences in intervals, we need to set a soft constraint to adjust pitches to fit the accompaniment. Therefore, we have designed a state transition model with time-varying probabilities, where the probabilities control the pitch motion. The model accepts a one-hot vector representing the previous pitch and outputs probability to reach the current pitch. We can control how rigid the constraint is by the variance of the probability distribution. We have hand-tuned the parameter through experiments. To maintain consistency, we have also constructed a probabilistic model. Maintaining consistency requires constraints on pitches by the accompaniment. This requires us to consider relatively long-term dependencies on pitches and chords. As it is well discussed in music generation and harmonization tasks, we can apply a neural network to cope with this issue. We have used bidirectional RNNs with LSTM cells, where the network accepts pitch profiles of the accompaniment and outputs probability for each melody pitch. Finally, to achieve both the melodic contour and the consistency, we formalize this issue as an optimization problem to maximize the following objective function. The objective function mainly consists of two terms, probability Q from the contour model and probability P from the consistency model. By adding two log probabilities, the value of the objective function indicates how well two types of constraints are jointly satisfied. We have introduced a parameter lambda to balance two constraints. By maximizing this objective function, we can obtain the desired sequence of pitches. The actual procedure for optimization is to search the pitches that maximize the objective function. This is equivalent to finding an optimal path through lattice structure, where the horizontal axis is the index of melody notes, and the vertical axis is the MIDI node number. The contour model provides a transition probability between notes, and the consistency model provides the emission probability. To find the optimal path, we can apply dynamic programming. Okay, so in the experiment, we have observed how conversion can avoid two unwanted scenarios. One of the scenarios is that the melody preserves the melodic contour, but does not fit the accompaniment. The other case is the melodic contour being drastically changed by maintaining the consistency. To check these cases, we have used two evaluation metrics. One is the root mean squared distance to compare intervals of generated pitches and the original melody. The other is negative log probability divided by the length of the melody. This measures how likely to observe the generated pitches given the trained consistency model with the training data. We use the MIDI files of popular music from the RWC music database. We first trained the RNN parameters of the consistency model, and then tested the method with the melodic contours, which are not from the training data. We tried 90 combinations of melodic contour and accompaniment, and calculated the two evaluation metrics. This figure shows the evaluation results. The left vertical axis indicates the root mean square difference, and the right vertical axis indicates the negative log probability. The lower, the better for both metrics. We can see the root mean square difference decreases by increasing the parameter lambda, and the negative log probability increases. This figure indicates several melodies generated by different values for lambda. The baseline denotes the original melody. We can see that the dotted line with lambda 0 does not preserve the melodic contour at all. However, by increasing to 0.6, the rigid line with circles resembles the melodic contour of the original melody. The experimental results indicate that contour-preserving melody conversion provides an intuitive tool for computer-aided melody composition. It enables reusing the melodic structure And the composer can balance between strictly preserving the melodic contour and maintaining consistency of melody and accompaniment. Our future work includes considering phrase boundaries in extracting the melodic contour, generating rhythm variations through conversion, and the listening test of the generated melodies. In conclusion, we have proposed contour preserving melody conversion for an interactive computer aided melody composition. Thank you very much for listening.